right, welcome to your lecture on depth perception. In the video clip here on the front page, we have an art installation that, when viewed from a particular angle, appears to have depth, right? It appears to be looking, instead of protruding from the wall, actually looks like we're looking down a corridor. Pretty cool stuff. So, we're going to talk about double vision too, hence our music, binocular vision, and let's just jump right in and get started. So we left off last time talking about figure ground separation. So in this adorable picture of my two young kids, what object is in the foreground, is the closest to you? Okay, hopefully everybody said my daughter Jenna, right? How can you tell that she's in front of Taylor? Right? How do we tell if something has depth? What are cues that we use? Right? We use a lot of cues, right? So one cue is that she is occluding him, right? And this actually is learned, right? We can see that he's behind her, right? How big do you think that boat is behind my son Taylor? Looks like, Taylor was probably about a foot tall, so I'd say it's probably about 6 inches, right? No. So it appears much bigger, right? Like maybe 8-10 feet, because size and depth are related to one another, right? So the further away something is, the smaller it appears, right? And we learn that. Obviously, we weren't really at the beach, right? So this is a backdrop in a photo studio, but we can initiate cues of depth or the feeling of depth in pictures by how we arrange objects and what their perspective is, right? So the first types of cues we're going to talk about with depth perception are monocular cues. This means that they work the same with one eye as they do with two, right? You only need one eye to see monocular cues of depth. The second half of the lecture, we'll talk about binocular vision and binocular cues that you need two eyes in order to perceive. These are also sometimes called pictorial cues because they can demonstrate depth in a two-dimensional object, right? In a picture. They can convey depth in a picture. All right, so if we look at this picture, right, which cloud is the furthest away? The one on the left or the one on the right? Okay, which person in the picture is furthest away? The one on the left or the one on the right? Okay. These are called relative height cues, right? So if something is below the horizon, like the person here, the higher they are, the closer they are towards the horizon, the higher they are in the picture, the further away they appear. Now, what's wrong with the depth cues of this person? The relative height is there, but the size doesn't change. If we really wanted to initiate a depth perception, then we would have the size of the person getting smaller as they get higher in the picture. We do see that with the objects above the horizon, right? So I'm sure everyone said the cloud on the left is furthest away. The closer things are towards the horizon, the lower they are in the sky, and the smaller they are, the further away that they appear, right? So here, which rabbit is the furthest away? Right? The smallest one that is the highest in the picture, right? And the closest rabbit is the rabbit down here, right? You would perceive the rabbit here that's furthest away as being approximately the same size as these rabbits. However, this rabbit appears much smaller, right? When in reality, this rabbit and this rabbit are exactly the same size. It's their relative height that allows us to think of this as being bigger because it's further away. So depth and size are integrally linked together. Okay, of these three cars in this picture, right, which one is the biggest? The one that's at the top of the picture, right? Okay, what I want you to do is to reach out with your fingers, right? Measure that car, and then don't move your fingers and measure the second car, and then measure the bottom car. Can you prove to yourself that those are all exactly the same size? But because of the way that they are the same size, but because of occlusion and because of relative height and because of the placement on the street, it appears that the depth perception tricks our mind into seeing that top car as being much bigger than the other cars. Pretty cool, huh? All right. In this arrangement, right, we have no problem telling which glass is in front, right? Right here, because of occlusion and because of relative height, we know that this glass is in front of these other glasses, right? But cues can conflict, right? So what if we switch this and now we occlude this cup with this vase, but relative height is saying that it shouldn't be occluding that cup. It almost looks like the cup bends around behind the vase in some way, right? We can resolve that, right, by putting a shadow in there, and all of a sudden we're like, oh, that vase is floating in the air. That's why it's occluding that cup. It actually is in front of the cup. All right, so that cast shadow extends the relative height down in front of the cup, and it resolves the conflict for us. All right, so here, who is closer to us? Right? Again, if we put in shadows, right, we can see that these people are exactly beside each other. So the woman is running and in the air while the man is standing on the ground because of the cast shadows. Right? All right, so relative size is a cue that we can use to tell how far away something is if we have a sense about how big that object is. So here we see a golf ball, a baseball, and a basketball. And on the retina, this is the inverse projection problem, right? All three of those are exactly the same size on the retina. So if all three of those are the same size and we know what those objects are, then we know that the basketball must be much further away than the baseball, and the baseball must be further away from the golf ball, right? Again, in this picture, we can tell based on relative size that how far away these balls are, that the two balls on the right are approximately next to each other. Maybe the relative height suggests one's a little bit further away than the other, and then the smaller ball on the bottom. Another monocular cue that we use to tell how far away something is aerial perspective or atmospheric perspective. So here you can tell that the building behind the varsity sign is several blocks away, right? Because of relative size, but also because of distortion of the details in that building based on the atmosphere. So remember we talked about color. We talked about the Blue Ridge Mountains and how when there's a lot of perspective or atmosphere in between two objects that it takes on that bluish tint because we're looking through the atmosphere. Same thing here. So we can initiate in this image down here a perspective of depth by simply changing the shades, by making these less clear and lighter the further away they get as they have relative height. Linear perspective refers to the fact that parallel lines will converge in the distance. So here in this painting, we see the tiles on the floor. And not only do the tiles on the floor, these lines start to converge to a point, right? We also lose detail, right? So we have a texture gradient. The further away objects are, the more densely they appear. And we lose detail the further away something is. All right. So here are two more examples. A classic example of railroad tracks that appear to converge. We know that they're not getting closer together down here. And also we see texture gradient, right? So the railroad ties, you can see clearly here, the further away we get, the less detail, they become very densely packed, right? We can initiate a perspective of depth here through relative height, changes in size, and density. Texture gradients are very important because they provide information about how far away things are based on the appearance of the ground, right? If we were to remove the texture gradient from the ground, then we become less accurate at perceived depth and how far away something is. And in fact, we actually tend to overestimate how far away something is. Why would we do that, right? So here we can see when there's no gap between the person and the target, people are really good at estimating how far away that is. However, when there's a gap here, all of a sudden this appears to be further away, right? So if you were going to jump across that gap, right, you would want to jump further than you think you need to, right? So there's sort of an evolutionary advantage into overestimating if we can't perceive depth. All right, there are some movement produced cues on depth. This is still monocular. You still only need one eye to see these. And the first one we're going to talk about is motion parallax. Right? This is the, I'm sure you've noticed this. This is the illusion when you're riding in a car down the interstate and objects that are very close to you appear to move very fast and objects that are further away appear to move slower. And we'll see a video on this in a second. But essentially in the same amount of time, position object A, as we move from position 1 to position 2, travels much further across the retina than object B, which travels a shorter distance, right? That makes object A appear to be moving much faster because speed is how far you travel over a certain amount of time, right? So here, if we have from A1 to A2 is 6 centimeters in 1 second, B1 to B2 is only 2 centimeters in the same amount of time in 1 second, right? So that appears to be moving 3 times as fast, object A does, than object B. Another type of movement cue is called accretion and deletion. So as I put this little yellow man walking down the road in front of Old Main here, we can tell that this person is located on the road, right? Because it is accreting and deleting as it provides occlusion. So this is basically accretion and deletion is occlusion with movement, right? And if we come in and put another giant red person over here, right, we can tell that that giant red person is behind the tree, but in front of Old Main, right, because of the accretion and deletion. Okay, that's it for monocular cues. Now we have some ocular motor cues where we actually get feedback from our ocular motor muscles, right? So as something becomes closer to us, we have to converge our eyes together in order to keep that focused, right? Okay, let's try this exercise. I want you to hold up your index fingers, right? I want you to put your left one as far away as possible and your right one about 2 or 3 inches from your nose. Focus on your left hand far away, and then I want you to focus on your right finger and notice your eyes moving. Okay, focus on your right finger, go back to your left finger. You can feel your eyes converge in and then relax as we get further away, right? You remember when we talked about accommodation. Accommodation is another ocular motor cue. So not only do our eyes converge, but we have to fatten that lens so that we can keep the image focused on our retina, right? So convergence and accommodation are good cues, but they only work for objects that are about 3 to 4 feet away from us. After that, there's not much movement, enough movement that we can detect those signals. And so that leads us to binocular vision. So we did monocular cues, ocular motor cues, and now we have two eyes, cues that we need two eyes for. Binocular vision occurs because we have a large overlap of our visual fields. So our fovea, all of our fovea, a large section of our visual field can be seen in both eyes. In fact, you can do that if you hold your hand here, right? And cover your left eye, move to the right. So like right about there. If I do it with my other hand, right about there. All right, so my field of vision is about that far at that length, right? That I can see overlap in each eye. So because we have overlap and because each eye is seeing a slightly different perspective, right, we are able to generate a three-dimensional image. So, and this difference in the angle between each eye is called binocular disparity. So here we see an image as if our left eye and right eye see that. And you'll notice that you see slightly different things. So our right eye can see more of this spike rider than our left eye can. Our left eye is seeing more of the building here, where here in the right eye it's occluded, right? And so this difference, this binocular disparity, helps with depth perception and also generates that three-dimensional image. I really wish that we were in person today because I wanted to be able to pass around. Well, I probably shouldn't even do that with all the COVID. We'd have to wipe it down in between each use. But did any of you have this toy when you were younger? It's called a viewfinder. And you have these little wheels, discs that you put in there. And when you look into it, right, you see a three-dimensional image. And in fact, I took a picture of what I'm looking at, which is Thomas the Train here. And so this is what is being shown to the left eye and to the right eye. And you can see that the picture is slightly different. I know it's not great in focus, but one of the ways you can see it's different is you see how far this telephone pole is from the side of his face. And here you see it's much closer, right? So there's slight differences. And that presenting these slightly different images to each eye is going to generate that three-dimensional image. Viewfinder, fun stuff. All right, so the stereoscope was another example of that, right? Where you could flip back and forth between two images or free fuse your eyes to create binocular disparity, which then can generate that three-dimensional image. So this is figure 631 in your book. It'll be easier to do on your book than the screen, but if you can cross your eyes while you're looking at it to create a middle image. So you actually now have three, there's a middle image. When you do that and fuse it, the three white squares line up one in front of the other, and there's a perception of depth there, so that the square at the bottom is closer than the square at the top, right? And there's a couple of examples of this, right? Say this is how 3D movies create the illusion of depth. You have to wear those glasses. Those glasses have polarizing lenses in them, and so you're actually seeing two slightly different images in each eye based on the polarized light. Random dot stereograms create depth the same way, and we'll talk about how that happens in just a minute when we talk about corresponding retinal points on the retina. All right.
Hey, Vsauce! Michael here. This is called the dolly zoom effect, and the optics that make it possible are also responsible for what's called the moon terminator illusion. A terminator is the line between an illuminated and dark side. Light arrives perpendicular to the terminator, but it doesn't always appear to. Maybe you've noticed this before. When the moon and the sun are up at the same time and a good distance apart in the sky, the direction the moon is being lit from won't always appear to line up with the position of the sun. What's going on here? The answer lies in visual angles. The further away from you something is, the smaller it will appear to be. In psychophysical terms, its visual angle shrinks, the angle within your field of view that it stretches across. Now, this means that everything we look at is foreshortened. That is, it diminishes in size towards the horizon line, a line infinitely far away. Things that far away are foreshortened to the point at which they have no height whatsoever. This distortion affects everything that we look at, but it doesn't confuse us because our brains know about it. We can look at an object that is foreshortened and figure out what it probably actually looks like. For example, a door is a rectangle, but it's wrecked by foreshortening when opened. Closer distances appear larger. The whole shape is different. But your brain isn't freaked out every time a door opens because it understands that different sensations don't necessarily mean different actual things. It's called subjective constancy. Our brains cleverly factor in previous experiences and perspective clues from the surrounding world to calculate in real time whether changes in what we sense are because of actual changes in the things we're looking at or are just merely products of their positions or the surroundings. For example, I, right now on this video screen, am vulnerable to foreshortening, but I probably look okay to you. However, if we frame in really closely and remove surrounding perspective clues, I can be made to look weird, strange, a little scary, distended. I'm foreshortened without the necessary tools around me for you to mentally adjust. This is probably the crux of the moon terminator illusion. Take a look at this. The line where that wall meets the ceiling is a straight line. Seriously, take a look. If you look to the left and right, it continues to look straight. And trust me, this building was built with level, straight ceilings, but that's not what your eye senses. A camera will help demonstrate this. It doesn't add in the post-sensation processing that our brains do, and we can also frame in to remove other clues telling us what to think. Now, sure enough, right in front of us, the line is level with the screen of the camera. It's a straight line, but if we move our eyes across the line, look what happens. If I pan this way, the slope changes, and now the line appears to be going up and to the left. And if I pan this way, the line appears to be moving up and to the right. What's going on here? A straight line can't have changing slope. That's what a curved line does. Just like the curve we think we see between the sun and the moon. But wait, if the line between the sun and the moon is curved because of foreshortening, why don't we see lines like this one as curves? Well, here's a clue. Clues. We know what rooms are supposed to look like. We know how they're built. We have experience with them, and there are other things in the environment helping us. But when you look at the sky, there's not much to help you. In the absence of clues about distance and perspective, our brains assume that whatever we're looking at is equidistant from us, making the sky a sort of dome surface, like a planetarium screen. The only clue we have then is the horizon, but it's a red herring, because the horizon doesn't foreshorten. It's just a place where, due to foreshortening, everything becomes infinitely flat. Brian Rogers and Olga Naumenko demonstrated that these things result in the Terminator illusion by using a planetarium. They projected 2 dots onto its dome, mimicking our perception of the sun and the moon. They then asked participants to place a 3rd dot on the straight line connecting them. But just as in the Moon Terminator illusion, people incorrectly placed the 3rd dot. They were influenced by a desire to stay parallel to the horizon, as if it was subject to the same foreshortening rules. Our brains also often fail to factor in foreshortening when it comes to crepuscular rays, light beams streaming through gaps in clouds. They appear to converge from a common point, as if the sun is only a few thousand meters above Earth. But of course, in fact, the sun is extremely far away, and these lines are actually pretty much exactly parallel. It's true. They look like they converge for the same reason railroad tracks appear to converge. The visual angle of the distance separating them shrinks the further down you look. Sometimes our brains do the opposite. They assume and consider foreshortening even when it isn't really there. Like in this illusion, where the cars seem to be different sizes, but in actuality on the page are all the same size. Everything else in the image is affected by foreshortening, so our brains assume that the cars are too, and decide that in order for them all to have the same visual angle, which they do, the more distant ones must be literally larger in real life. The rate at which the visual angle of something you are looking at changes as you move toward it or away from it is not constant. In order to cut the visual angle of an object in half, its distance from you must double. That means objects really far away require a lot more movement to have their visual angle changed compared to nearer objects. This is called parallax, and it's a major reason moving allows us to learn so much about depth. It's why stuff on the side of the road whizzes by you as you drive past, while distant features of the landscape appear to only crawl past. A really distant thing, like, say, the moon, 384,000 kilometers away, appears to move so little as you do, it can seem to be following you. It's not, of course, it's just geometry. For the same reasons, moving a camera through space will affect the visual angle of nearer things, like the Vsauce mug here, much more dramatically than distant things, like Jake Chudnow's album Against the Wall. It is barely changing size as we move back and forth. But unlike moving, zooming increases the visual angle of everything equally, regardless of depth. Notice that when zooming, the distant album grows and shrinks right along with the mug. Now, if you move in while zooming out, or vice versa, the zoom will be most apparent when looking at distant things, while the move more apparent on near things. The result can be trippy. Here, I've been placed where both effects cancel each other out, so everything around me changes instead. Another great illusion that takes advantage of parallax is the popular star field or hallway illusion. Cover the middle of the video and you'll appear to be moving much faster. But if you cover the edges, you'll appear to be moving much slower. All you're doing is altering the perspective clues your brain receives about movement. The nearer stuff at the edge changes position faster than the distant stuff way ahead. So if you cover the slow distant stuff, your brain only has the faster moving stuff to judge speed from. But cover the faster near stuff, and the slower stuff becomes the new near. Your brain assumes that you've slowed down. The optics and mathematics behind all of these effects were understood at least thousands of years ago. During the Renaissance, artists used that knowledge to produce paintings that imitated reality really well. I mean, the perspective is quite realistic. But the Renaissance? Why did it take so long for us to get there? I mean, look at this pre-Renaissance painting. What the heck is going on here? The perspective is all wrong. That's not at all what such a scene would actually look like. Artists and viewers contemporary to works like that saw the world just like we do. They saw foreshortening, they couldn't help but see it. Foreshortening is right there in plain sight. No, foreshortening is plain sight. So, what gives? Were medieval artists all just a bunch of 5-year-olds? No. No, in the sense that the question is wrong. Realistic looking perspective was used way before the Renaissance. Now, it might not have always been mathematically formal perspective, but foreshortening was understood. Western art went from this to this, not because humans all of a sudden became smarter, but because of a difference in desire. What to us today might look unrealistic and thus bad, was in its time deliberate and popular. The shift to imitating the world mathematically, as if seen through a window, was more about cultural interests in objectivity and the individual than it was about artists all of a sudden becoming smarter. Furthermore, perspective illusions show us that what we think we see isn't always what we're seeing. A child's drawing may seem crude in terms of objective mathematical imitation, but there are other things about the world and our experience of it worth imitating. Teasing out the less plainly obvious to show something personal is sometimes even harder than following perspective grids. Picasso put it this way: "It took me 4 years to learn to paint like Raphael, but a lifetime to learn to paint like a child." And as always, thanks for watching.
Okay, we're back. So, after that video, I recorded the rest of the lecture, but my microphone didn't work. So we're going to try round 2 here. I am going to be so happy to not talk to this webcam anymore and be back in person with you all next week. You cannot even believe it. All right, perceiving size. Size and depth are intricately linked together. We just saw that in the video clip. When we lose depth perception or lose relative size perception, then that affects the other one. So we can talk about a whiteout condition where, say, this helicopter pilot is in a snowstorm or it's very foggy, and he doesn't know his altitude, and he looks down and sees what he thinks is a dump truck, but it's really a brick on the ground, right? So if he perceives that visual angle as something very large, then his perception is going to be that he's far away, that there is a long distance there, right? So based on having similar visual angle, if the visual angle is held the same, that means the retinal image is held the same, then what affects our perceived size is our perceived distance from that object. So the visual angle becomes very important, and the fact that different objects of different sizes at different distances can produce the same visual angle, therefore making the same identical image in the retina, is that correspondence problem that we talked about last time, right? Movement helps to figure that out, because things that are far away are going to move at a different rate, the parallax, right, than things that are up close. Okay. The sun versus the moon. What is the perceived size of the sun and the moon? Do you perceive the sun and the moon to be relatively the same size up in the sky? What happens during an eclipse, right? So you remember the eclipse a couple of years ago, right? The moon covered up the sun fully, right? So the perceived size is the same of those, right? So this is all based on visual angle, right? So it turns out that the visual angle for the moon is about 0.5. The moon is 2,200 miles in diameter and is almost 250,000 miles away from us. The sun, much, much bigger, almost 900,000 miles, 865,000 miles across in diameter, right? But it's 93 million miles away. So it's much, much bigger, but much further away. What happens is that then generates exactly the same visual angle, which is why it appears that the moon can fully cover up the sun, even though it's a fraction of the size of the sun. All right, speaking about the moon, does the moon always appear the same size? Or have you ever seen the moon and you're like, wow, there's a really big moon tonight, right? What about these two pictures here? Do the moons look the same in both of these images? Do they appear to be the same size? Think about a time when you saw the moon and you thought it was really big. Where was the moon? All right, so let's do an Ed puzzle here. How many people think that the moon on the left is smaller than the moon on the right, bigger than the moon on the right, or the same size as the moon on the right? Okay, let's find out the answer. There's a circle around that moon. Same exact circle, right? So I'm betting most of you felt like the moon on the right-hand side was larger than the moon on the left-hand side. So why is it that when the moon is high up in the sky, it appears smaller, and when the moon is closer to the horizon, sometimes it appears very, very much bigger? Is the moon closer? Does the size actually change? No. So why does our perception of the moon change? Well, it's based on environmental stimuli or the lack of environmental stimuli. When we have a reference point of the horizon, of mountains, of trees that are a known distance away, we're a better judge of the perceived size of the moon. However, when the moon is in the middle of the sky, like it is on the left-hand side here, and we don't have a very good ability to compare it to other things that are a known distance away, we underestimate the size of the moon and it appears smaller. This is that foreshortening that they talked about in the video that we just watched, where even though the moon has the same visual angle and the same stimulation on our retina, when it's vertical, we have that foreshortening or flattened heavens illusion. We think that it is further away than it is, and so therefore it appears smaller. Whereas when it's up against the horizon, which is a known distance away, we think it's closer to the horizon, therefore much bigger. All right. Perceived as bigger due to heuristics involving the horizon and other size cues. You can test this yourself. The next time that you see a moon, you say, wow, that moon's really big. Take a picture of it with your phone. Don't zoom in, just take a regular normal picture, and then later that night or the next night when the moon's high in the sky, take another picture of the moon. And if you compare the size, if you measure the size of the moon on those pictures, it will be identical, I promise you. Okay, so heuristics of size perception. Even though we have some things like the flattened heavens illusion, where we judge an object as a different size depending on cues, right? Usually we have, given the availability of depth perception, the size of objects remains fairly constant. And in fact, there's a size distance scaling equation where S is the perceived size, there's a constant K, we don't have to worry about that. And then you have the actual retinal image and the perceived distance from the retina, right? So if we think about the flattened heavens illusion, the retinal image is the same, right? The moon doesn't change size if it's straight up and down right above us or if it's at the horizon, right? But our S perceived size changes because we think that the distance to the moon is much further when we have cues, right, than when we don't have cues. Okay, here's a wagon wheel, right? If I were to have you guess how big this wagon wheel is, you probably would guess, up to your waist or maybe your chest, 3-4 feet, something like that, right? Because we are familiar with wagon wheels, right? Then what if I uncover this side of the picture? Now, what is your perception of this wagon wheel? Now your perception of this wagon wheel is that it's 10, 12 feet tall, right? Because we gave you a familiar object. So you recognize that, hey, wagon wheels could be bigger. People probably aren't that much smaller, right? Because if that was a 4-foot wagon wheel, that grown person would have to be 2 feet tall, right? And that just doesn't match with the perspective, right? So we can use cues that we're familiar with in order to judge size.
Does what we see correspond to what's really out there? Or does our brain construct its own version of reality, one that does not always match up with the physical universe? Check me out, for example. I am the same size here as I am over here, but over here I look much larger. No, it's not a cheap video trick. It's a trick on your brain. Here's what you're seeing. The me over here is indeed projecting a smaller image onto your retina, the region of light detecting cells at the back of your eye. All else being equal, smaller images mean smaller things. Here, I'm in no danger of hitting my head on the ceiling. But over here, I am ducking. Ceilings are useful visual landmarks for judging size. Of course, you're making these size estimates based on the assumption that this room is ordinary and box-shaped. You assume the back wall is perpendicular to the line of sight, so the two versions of me are the same distance away. You're also assuming that the floor and ceiling are level and parallel. But as you probably guessed, this isn't the case, and the room isn't box-shaped at all. It's trapezoidal. The back left corner of the room is much farther away than the right. Since I'm farther away over here, my image is smaller, although I'm definitely not. The ceiling cue is also misleading. The floor actually slants upward and the ceiling downward from left to right, making my head much closer to the ceiling when I'm over here. Why couldn't you see these things and adjust your size estimates? The room's features have been cleverly distorted to be consistent with a rectangular shape. The checkerboard pattern on the floor gets finer grained toward the right, so that the same number of pattern elements fit in a shorter distance. The windows are resized and shaped to match the trapezoidal back wall. Your narrow angle of view from the front of the room blocks the cues that would reveal the room's true shape. And of course, we easily believe in a box shape because that's the shape rooms normally are. This clever setup is called the Ames illusion. American ophthalmologist Adelbert Ames Jr. devised it in 1934 and built a physical example the following year. For Scientific American's Instant Egghead, I'm Ingrid Wickelgren.
Okay, that's a great description of the Ames room. So let's apply the size distance scaling equation to this illusion. Here we see the same girl, right? But over on this side, she looks like she's about, 4 feet tall. And on the other side of the room, she looks like 8 feet tall. As we just saw in that video clip, she is indeed further away on the left-hand side, but our depth perception stays the same. So there's a smaller retinal image on the left. So we have a 3 here, right? And a bigger retinal image here because she is in fact closer, a 5, but our perceived distance doesn't change because of the illusion of the room. So 3 times 5 is 15, 5 times 5 is 25. That's how we get a difference in perceived size. Okay, we're going to shift gears, and for the rest of the lecture, we're going to talk about binocular disparity. This gets a little bit tricky, a little confusing, so maybe it's good that it's on video so that you can pause it or back it up or go rewatch it later if you look at your notes and you're somewhat confused. So if we have 2 points in space, A and B here, they are going to project on 2 points on our retina. Because they are not even with one another, because B is further away, the difference in between the distance between B and A on the right eye is going to be greater than B and A on the left eye. This is called retinal disparity. And our brain is very good at measuring this. In fact, we can detect a difference of 1 micrometer difference on the retina that helps allow depth perception. If we were to move point B up to be the same distance as point A, that would then change the distance on the retina so that now B and A would be the same distance apart. We would have 0 disparity, and they would be at the same depth. Now that blue line represents our plane of focus, and it's not actually a straight line. Why wouldn't it be a straight line, our plane of focus? That's right, because the retina is not flat. The retina is curved, so that makes the plane of focus actually a curved arc. We call that arc the horopter. It also is sometimes called the Weissmuller circle, and it is the plane of focus where images are falling on corresponding retinal points. There's 0 binocular disparity, and everything in that plane of focus is equidistant from us. It's equidistant from us, right? So in the image above, the lifeguard's looking at Ralph, while Susan and Harry are also in the horopter, so they are an equal distance away from her. Carol and Charlie are going to be falling on non-corresponding retinal points. There's actually a region of fused images that are falling on those corresponding retinal points, and we call that the plane of fused area. And convergence and accommodation allows us to move our plane of focus in and out. So if you remember, convergence and accommodation pretty much stop about 20 feet away. So everything 20 feet and longer, our plane of focus is pretty static, and we can't really use non-corresponding retinal points to detect things. When objects are not within that region of uncrossed images, it creates diplopia, or double vision, because those things are falling on non-corresponding retinal points and they don't get matched up in our brain. All right, we can try this. Take your left hand, put it as far away from you as possible. Take your right hand, put it a couple inches from your nose, right? And I want you to focus on your left hand. How many of your right finger are there? 2. Now focus your plane of focus on your right hand. How many of your left hand are there? 2. So what we're doing is when you focus on one of those fingers, you're putting it on corresponding retinal points through accommodation and convergence. And the other one is on non-corresponding retinal points, and therefore we see 2 of it, double vision, right? Here's another example of that where we can see that the blue and red points are falling on B and B prime, F and F prime. Those are corresponding points. However, things behind the horopter are falling on A and D prime. They don't correspond, therefore they don't match up in the brain, therefore we see 2 of them. And the brown point also falling on C and E, right? If we were to move the green point up into the horopter, where it was falling on the retina would shift and would line up on matching corresponding retinal points. Okay, meet Bob and his magic floating crayons. It's kind of a weird example, but it comes straight out of your textbook, so I'm going to use it. The only thing different is I've added the horopter there in green on the right-hand side. So our eyes, as I mentioned, are really good at measuring this relative disparity. That's how different are the images on the left and the right eye on the retina. How far off of corresponding retinal points are they? So if we look here, the red crayon is on the horopter, and it is actually in the fovea, if we look at these points, right? Blue looks like it's also on the horopter. It looks like it's in about the same spot in the left retina and the right retina. However, the purple is clearly not in the same spot, and the brown doesn't look like it is either. So if we're to superimpose the left and the right image into one, right, we can see that there's a greater difference in disparity for the purple than there is for the brown. That means the brown is closer to the horopter and the purple is further away. The greater the relative disparity between the two eyes, the further away from our plane of focus. Right? Here's another depiction of that, looking at the having blue and red on the horopter, and then seeing how far off the purple is compared to the brown. All right, what about differentiating between in front of and behind? Now we now have a way to measure how far away from the horopter is an image, but what about if we want to know is it in front or behind? It turns out that yes, we can do that. So if I were to put a green dot in front of the horopter, it would actually produce cross disparity, whereas the things behind the horopter we call uncross disparity. So what am I talking about? Cross disparity is in front of the horopter. So in point A, we focus in figure A, we focus on the red object. That makes the blue object in front of the horopter. That puts the image on the inside of each retina. So we see the left retina, right retina, the blue is on the inside part. However, if we have uncrossed disparity and we now focus on the blue point, the red is behind us, we have uncrossed disparity. Now, the item that's in focus, the blue one, the disparity item is now to the outside, right? We call that uncrossed. So you kind of think about like cross-eyed, if it's on the inside towards the nose, it's cross disparity, that's closer, cross-eyed. Uncrossed, it's going to be on the outside of the focus thing. Here's another depiction of this. And not only do we have the crossed versus uncrossed disparity as a signal if it's in front of or behind the horopter, how much it's crossed or uncrossed. The size of the disparity indicates the distance from the horopter. So now we have a way to measure or understand how far apart different objects are based on these cues. Most of our knowledge depth perception is psychophysical, not physiological, meaning we're looking at where things are projecting on the retina. We're asking people, what do they perceive? Where's their fixation point? We have them change their fixation point, see what that does to aligning things on the retina. And that's because all of the processing of this signal is happening in the cortex. And it's a very complex processing. There isn't a specific area devoted to depth perception. It kind of happens across areas. We can find simple cells in the cortex that respond to zero disparity and then respond to other degrees of disparity, right? So zero disparity meaning that object's now in the horopter, or greater disparity meaning that it's not either crossed or uncrossed. Okay, so here's an example of a zero disparity cell in V1, a simple cell that has a tuning curve. It's going to respond the most when cells are on those corresponding retinal points, and it responds less the further crossed or uncrossed those non-corresponding points become. We can also find similar neurons in V2 and middle temporal cortex, and also in the ventral pathway. They're spread throughout the pathway, helping us define depth and define the placement of these points. The other thing that makes this very difficult is we're showing this example with a fixation point, but that fixation point can change, right? We can move our horopter in and out. And so, hardwiring this system to always have the same zero corresponding points is difficult. Here we have cells where, based on a fixation point, items that are in front of the fixation point are going to be stimulating non-corresponding points that hook up to a red neuron in the brain that's going to say that's in front of your fixation point. Items that are behind the fixation point are going to be stimulating the non-corresponding points that project to the blue neuron, which says that things are beyond the fixation point. There's another example of that. Again, The P is in the plane of zero disparity, so it's falling on corresponding points, whereas the Q on the left side is falling on the P, is lined up with the P, but is falling on the Q on the right. So these are non-corresponding or disparity cells. So we would have to have connections from the corresponding sites projecting to the zero disparity cell and other connections from the P and the Q from each eye projecting to a binocular disparity cell. So you can see how this is really complicated, right? But it's part of understanding how we can resolve that correspondence problem by understanding depth perception. Again, if we were to move our plane of focus up to Q, now that would shift Q to be projecting on Q and Q prime, and P to now be projecting on Q and not P prime, right? So then those images shift from a zero disparity cell to a disparity selective cell, right? So the wiring of this is very complicated, very complex. So that makes it difficult for us to work out the details in the brain. All right, so having this correspondence problem where multiple things, right, multiple stimulations on the retina could arise from different things allows us to be able to create a three-dimensional perception from a two-dimensional pattern, which is called a stereogram. Sometimes it's also called a random dot stereogram. Sometimes they use random dots to hide the disparities. Sometimes they use patterns to hide the disparity. You've probably seen this. This is like the Magic Eye books, right? So what it is we have two random dot patterns, except some of the dots in there are not random. So we have these two yellow patches that are matched up with one another, and they're offset from one another in the left and the right image in a way that when you shift your horopter beyond the actual screen, you cause those two yellow points to match up and form a three-dimensional image, to fuse together as a three-dimensional image that's seen beyond the actual page. You can try that here. If you get your horopter and focus slightly beyond the screen, you can find a stereogram image. There's a sphere, there's a cone, there's a cube, right? And so once you get that image, once you sort of lock into the stereogram image, I want you to cover an eye and see what happens. And what you'll note is the image goes away because this is a binocular cue. Binocular disparity requires both eyes. You lose that ability of that depth perception with only one eye. All right, so this is a nice table that summarizes some of the cues that we talked about today and what distances they work the best at. Occlusion and relative size work at any distance, right? But accommodation and conversion, those oculomotor cues, only work when we're really close up and we have to actually do that. Atmospheric perspective, right, only works for things that are very far away from us where there's a lot of atmosphere in between us and the object. Here's another table or sort of chart to help organize these cues for you. So all the things in yellow, those are things that you should be understanding the cues. So we have light-based cues, size-based cues, position-based cues as static monocular cues. We have cues, monocular cues that involve movement, like parallax and accretion and deletion. Didn't really talk too much about optic flow. We'll talk more about that next week in our upcoming lectures. And then you have your binocular disparity cues. All right, here are your review points. I'm going to give you another Ed puzzle question here. Like I said, halfway through this lecture, I'm really getting tired of talking to a webcam. I can't wait to see your bright eyes at 8 o'clock in the morning on Tuesday. We will, on Tuesday, have a review session. So please bring questions for me for exam 1. We'll have exam 1 on Thursday. Then the following week, we'll have 1 lecture and then exam 2. So we got to really be on top of this material. We will meet briefly for less than 30 minutes for lab. If your lab time is Monday, come on Monday. If it's Tuesday, come on Tuesday. This is the color vision lab. I'm going to explain how to do it, and then you're going to do it on your own. It's done independently. You don't need a partner, and I'll cover all of that in lab section. If for some reason you have a conflict and can't come to your assigned lab section, it's okay to come to the other one. Just let me know. I want to know that you're switching for that week to hear the instructions at a different time. All right, have a safe weekend. Don't get COVID, don't get quarantined. Let's all get back together in class on Tuesday.